Hello everyone. Today I want to talk about illuminating the dark data of critical infrastructure. My name is David Henthorn. I'm an associate professor of chemical engineering at Rose-Hulman Institute of Technology. That's in Terre Haute, Indiana in the United States of America. So the first question, what is critical infrastructure? Well, it's things like dams and power plants and factories, water facilities, chemical plants, nuclear facilities. These are all sectors of the economy where if we saw a major failure, then we would see very strong economic or national security concerns arise. In the United States, CISA, which is the Cybersecurity and Infrastructure Security Agency, helps oversee critical infrastructure, and it's operating under the Department of Homeland Security. At Rose-Hulman, we have a critical infrastructure laboratory, and there we study the modernization of control systems and how we can use data to make informed engineering decisions. So critical infrastructure relies on industrial control systems. So what's an industrial control system? At the heart of all critical infrastructure, we have physical units, things like turbines and reactors and pumps and all these sorts of things. Those have physical parameters like how fast it's spinning and what's its temperature and everything like that. So we have instrumentation that reads these physical parameters. What is the temperature? What is the pressure? What is the voltage? What are the RPMs? All that information streams to a computer system known as the industrial control system. That industrial control system reads in all that data and then makes important decisions or control logic, which it sends back to the physical unit saying, slow down or speed up, warm up or cool down, these sorts of things. So industrial control systems for many years were designed to be air-gapped. And what we mean by an air-gapped system is this. We have a number of interconnected pieces starting with our equipment, leading into the process LAN, leading into the control LAN. But there's a perimeter around all these pieces where no exterior connections exist. There's no input or output to any of these systems. So how do we access the data in these cases? Most of the times you need to physically go to the system and you walk up to it with a USB thumb drive. You sit down at the operator station and then you download the data to your USB thumb drive. You walk it back to your office and use your favorite spreadsheet program, say Microsoft Excel, and you can then analyze it there. And it's a very inefficient process, and it causes people to miss much of the insight into what's happening on an immediate or day-to-day basis. And it leads to a phenomenon known as dark data. So dark data means that we have immense volumes of crucially valuable data literally locked away with the control system in a data center closet somewhere. So the security methodology, our air-gapped system, ultimately hinders access to these important insights and engineering decisions that we could be making. So at this point, we have a couple of questions. How do we get our data out of our protected networks efficiently, yet safely and securely? And then once we have that data streaming, what do we do with it? How do we make informed decisions with it? And one of the most common use cases we have is what's known as a digital twin. And a digital twin is a virtual representation of our physical unit. So the physical unit has instrumentation and it's reading all the key parameters, all the key performance indicators of our physical unit. That's streaming then into a time series database. And that time series database, our historian, then can be on premises or it could be in the cloud. And then once we do that, we can build models off of that streaming data that represents what the physical unit is doing, but we do that out in virtual space. And then interested parties, whether they're model builders or partners then from industry or from academia, then can work with this, and they can work with a live streaming version then of our physical unit without any concerns about disrupting the critical infrastructure. So at Rose-Hulman, then our technology stack is based off of using Telegraf to collect data from our control system then, and then we send that data out to an instance of InfluxDB. So real quick, in the 1990s, work at Purdue University in the United States by Theodore Williams noted that there are natural levels that develop with industrial control systems, and this is now known as the Purdue model. The Purdue model then has become the accepted way of describing a defense in depth strategy of how we can set up a control system where basically our crown jewels, our most important assets, are down at level 0 of the equipment. These are the robots and these are the reactors or the turbines or something like that. And then a step up from that would be the controllers that are monitoring this and making sure that the level 0 equipment then performs adequately. And then we step up to a control network where the operators and engineers work. And then on top of that, an operation level. And then we're starting to work towards the enterprise network where everyday business occurs. And so bridging the gap between the enterprise network and most of the control structure then becomes a demilitarized zone. So the question becomes, if we're going to start to put a device in here that can do data collection and then stream that data to a time series database, where should we put that? And so one thought would be, could we put it down here with the equipment, either at level 0 or with the controllers at level 1, the process level? And so levels 0 and 1, Telegraf actually has a number of plugins that can talk to the common industrial protocols that you would see at this level, Modbus, TCP, Ethernet IP, and these kinds of different things. And so Telegraf actually can handle that and has a lot of plugins for that, or it's extensible enough that you can write your own plugin and work with these things. But should you? There are definite use cases why you would want to avoid this if possible. And so while Telegraf is actually capable of speaking many of those protocols, there are some disadvantages here. And they mainly center around the level 0-1 devices. Then these are very dedicated devices, and you should leave them to do their dedicated tasks as much as possible. Firmware on these devices is not updated very frequently, and so you could have potential security issues there. And so along those same lines then, most of those protocols that were mentioned have basically no security or authentication then built into them. And so it's best to leave these things buried as deep as possible in that defense in depth strategy. And so bring that Telegraf agent away from these devices whenever possible. Another thing is that you'd have to then use Telegraf then to connect and manage connections to many devices. If you can abstract that and move that up the levels a little bit more, then you can get away from those kinds of things. So let's say if we move our Telegraf agent up a little bit, either to level 2, the control network, or level 3, the operations network. So this would be a significantly better place to put it. And so at this point, let's talk about one of the main control languages that's spoken nowadays. It's referred to as Opc Ua. Opc was an acronym within an acronym, and is very much in the Microsoft Windows family initially. It stood for OLE for process control. So process control being like industrial control systems and things like that. And then OLE was object linking and embedding. It's sort of the heart of a lot of the Windows clipboard kind of technology. It would allow us to take an object, link it, and embed it somewhere. So I could take a Microsoft Excel spreadsheet and then embed it into a Microsoft Word document. And so this OPC communication standard then was based largely around Microsoft Windows initially, and it had different flavors, whether you're accessing data, DA, or historized data, HA, or alarms and events, and these kinds of things. Over the time, it's moved away from being tethered with Microsoft Windows, and it's become in the last decade then an open platform that works across all sorts of operating systems and all sorts of platforms. And so it's now known, instead of as OLE for process control, it's instead known as Open Platform Communications, and a link to OPC Foundation is there. Along the way, they also tried to unify the data access, the historized data access, and all these kinds of things under a single umbrella, and that's known as UA, the Unified Architecture. So this newer way of talking to these devices is known as OPC Ua. And if you have this ability, then this is a unique way to bring in more modern internet connectivity standards and security to your data collection schemes. And a big thing is that it aggregates all this disparate sources and protocols into one area that you can talk to. If possible even, then we'd be able to put the Telegraf agent then in the DMZ, and the Telegraf agent then would be able to speak with the OPC Ua server, and it'd be close to the enterprise network where you might have a historian or even broadcast out to the cloud if that is your goal. So the way this would work is the DMZ usually writes very specific firewall rules, and then we would allow the Telegraf agent then in the DMZ then to communicate with an OPC Ua server in the operation level, or alternatively, then you'd have the Telegraf agent in level 3 talking to an OPC Ua server in level 2 in control, again passing through a firewall and being monitored and all these different things. So real quick, a shout out to Factory.io. Another option besides Telegraf is Factory.io has a Node.js implementation of an OPC Ua logger dedicated to writing to InfluxDB. And it's a nice standalone program, and it contains some very industry standard techniques for handling data, critical infrastructure data, including periodically scanning or subscribing and then asking to be notified when changes occur. And there's different data compression methods that they use as well. And there's a link there. Factory.io, I believe, has given a number of presentations to folks interested in InfluxDB before. So InfluxDB and Telegraf in particular then has actually an OPC Ua Telegraf input plugin that you can check out. Alternatively, we have our laboratory has written our own OPC Ua plugin. We wrote it in the Go language using the GOPC Ua library for communication. We've been running it in production then for about 10 months now, and we use those same sort of industry standard data compression techniques that the Factory.io Node.js implementation does, along with some heartbeat techniques. And we use this then to collect data on our control system and broadcast it out to an InfluxDB instance. So why OPC Ua? Well, the big thing is right here, security. Okay, we can choose different security modes from relatively basic things up to completely modern standards. None of this exists on the side of typical industrial communication protocols. And so one of the big things here is that you can do security and authentication with OPC Ua. And so on that side, we can do none. We can ask for none, or you can do username and password, or you can start to use signing and encrypting options there as well. The other thing is that because it goes out and aggregates all these different communication protocols into one area, it actually works as essentially a browsable namespace that you can look through and you can find. In this case, I'm looking at a certain piece of equipment. I'm looking at its current value of a value, and then I get all this rich information that it's a floating data point, scalar with certain sampling intervals, and all these kind of things. And so it's a very nice modern standard that really helps skirt around issues with older industrial protocols. So now that we have the data streaming from our critical infrastructure up to a time series database, how do we use the data? Well, there are two major use cases of our data from critical infrastructure. The first one is, what are the key performance indicators right now? These are immediate things. They should have low latency, and they need to tell us what is going on with the process immediately right now. The other way we look at things is we pull historical data. What are the key performance indicators over some previous time range? And we can then do strip charts and these different things with them, and we can mine them and do analysis on past performance history. So let's look at the first one. What are the values right now? So as we start to develop these things, we could have our software clients then, they could go out and they could query the OPC Ua servers directly. And there are some concerns here. Generally, we don't like third-party clients then connecting to the control system in any way. And so we limit those connections to the OPC Ua server to mission-critical connections only. So another alternative would be these clients then can query or connect to the historian, so the time series database, and ask for the latest values, the most recent values that were published then. And then depending on the location, then there could be some latency to this. So if we have our historian then out, for example, in a public cloud somewhere, then there could be some latency to this, and that may affect some newer applications that we might see. But for dashboards and a lot of web apps, this is not a big deal. But let's look at some other use cases where this latency might be a problem. Students in my laboratory have been looking at next-generation human-machine interfaces, for example, augmented reality, and we have either headsets or tablets or phones, and these are devices that take in an image and then overlay process data that it's pulling then directly from either a historian, or we'll talk about a potential edge device case that we would use here. And the reason we would do this is processes and the things that are associated with critical infrastructure oftentimes have these hidden variables that are hard to visualize and see, and so we can overlay that with these human-machine interfaces. For example, how hot the thing is, or what is it composed of in terms of like chemicals or some sort of physical substance. So one way we've been doing it is we've been using the Telegraf plugin that has an output for Prometheus-style metrics. This is an HTTP or HTTPS endpoint where it's the host, the Telegraf host, and then /metrics, and essentially it's a website that would expose the current values that the Telegraf plugin is reading and publishing out to a time series database somewhere. And this is a nice, lightweight, low latency option, and this works well for on-premises clients. And we usually try to put that in the DMZ, and that gets you access to these, to the current values that you're reading in your critical infrastructure. And because of its location, it works for a lot of different use cases. So overall view here is that Telegraf is talking to your infrastructure, to your equipment, and then broadcasting and sending that data to a time series database for historization. We can pull that historical data, of course, but if you want immediate data, we can use this additional HTTP/metrics endpoint, and you can do some cool things with it. So since the metrics endpoint is located in the DMZ, then we have access to it in either the enterprise network or also in the level 3 operation network. And so people within the control zone would be able to use that metrics endpoint as a very lightweight, low latency way to access current values that we're seeing in the process. But also potentially some people in the enterprise network then would also be able to pull from those current values. While you're doing this, we're typically going to pass this metrics endpoint through a firewall. And so let's think of different ways that we can harden access to that /metrics. And so one of the easy ways to do that would be set up a reverse proxy. Use something like Apache or Nginx as a web server that passes that /metrics endpoint, and then we use the built-in authentication and logging feature or load balancing features of Apache or Nginx, and let that do the heavy lifting of things like authentication. And since we tend to log everything and try to record and monitor everything, then this is a great way to start building logs about who is accessing your critical information about your critical infrastructure. And this also leaves Telegraf then to focus on its tasks, which is talk to the control system and then send that out to the time series database. So the other use case is when I'm looking at for historical data access, so historized data. And here it's shown that we're typically pulling that data in from our time series database, and the one we use is InfluxDB. So what can we do with this data? On the engineering side, we typically look at a few different use cases. For example, we benchmark previous performance of our equipment so that we can start to identify outliers, looking for getting a good handle of what the process looks like when it's running, and so we can see anomalous behavior there. We can start to forecast future behavior as things start to change. Where does it seem like it's going to settle down? What's a new steady state for this? We can use it to predict when maintenance is needing. I can start to see that equipment is showing its age. We're starting to see it falling out of a certain performance curve. And we can make informed decisions on whether perhaps to upgrade or scale up. The best way to think about how we could make a major plant upgrade is by looking at our past historical data and then using that to inform us that we will need X amount of new purchase in capital or something like that. Another thing is we're able to identify correlations in engineering trends and get engineering insight into what's going on by looking at this historized data. And finally, we can also look at aggregating data from multiple and varied sources. And I'll give you an example of this. We were having trouble with some electrical behavior in our critical infrastructure laboratory. So we started pulling in weather data and then comparing them. And lo and behold, that when we saw certain types of weather patterns, then we were starting to see those anomalous electrical behaviors. And by pulling those in and having one source where we could store all this data and then we could compare them, we were able to find that correlation there. So we're currently teaching a course at Rose-Hulman in process analytics. And these course learning objectives for the process analytics course, they center on the collection and analysis of process data to make informed engineering decisions. Students in these classes, modern engineering students, kind of typically have exposure to Microsoft Excel. All of them have been exposed to Microsoft Excel. They're very comfortable with that. A little less, still very common, but a little bit less common than Microsoft Excel would be exposure to something, a programming language like MATLAB. A number of them will get exposed to statistics language like R, and fewer yet will be exposed then to Python, even though that seems to be the direction that most engineering departments are going. It's moving in that direction. And so we've adopted for our process analytics course, we start with the ability to do some calculations in Excel and then eventually move students towards Python. And we focus on building and growing the skill set of our students. And so we start with something that they're very familiar with, data in spreadsheets. Every engineer loves spreadsheets. And then we start to work instead with CSV files and the ability to make easily shared text files across networks and things like that. Then we start to build in ideas of, well, you don't need CSV files. You can start to pull in your own data that's been historized in a time series database, but you then have to get comfortable working with time series data and timestamps in these different issues then. And then we start to move to key performance indicators. Students start to work with dashboards and building dashboards. And of course, for our stack on that, we use InfluxDB along with Grafana. And then we spend the bulk of the time in this class working with interactive Python data notebooks, and we'll talk about those. So dashboards, this is a typical dashboard that students then would be working with. In this case, we're looking at reverse osmosis equipment then, where they're tracking flow rates in and out, and then tracking pressures in and out, and all these sorts of things. But we don't start there. We've learned that onboarding the students, getting them comfortable with dashboards, there's actually a very interesting use case that we can use to reach college students. And I've loaded 5-year historical data for the popularity of the top 100 games on the game aggregator called Steam. And Steam is, well, a publishing app that works to basically get and publish games, common games that, of course, college-age students like to play. So the students dive into that and they really mine the data to find the key performance indicators, and they start to build dashboards with those key performance indicators. So before they get into the hardcore engineering kind of stuff, then we give them a chance to play with something a little bit more familiar, Steam games, stuff like that. So almost immediately they start to understand concept, and they pick up concepts like seasonality of data. They realize that, okay, at certain times of the year, people play more games than others. But they also started to pick up and they learn to identify outliers. And then they start to mine through, like, why was this an outlier? Oh, this game got a major patch, and so people started playing it again to see these new features. Or in the case of early spring or spring of 2020, then they said, well, look at how many people then stayed home because of lockdowns across the world. And so we saw that the effect of COVID on gameplay. And so a typical dashboard that the students might have for their Steam games would look something like this. In this case, number of players as a function of time, and then gain, and these kinds of things. And they start to toy around with these ideas and get an idea of what the dashboards might look like. Then we move them on to interactive Python notebooks, and of course those are the Jupyter notebooks. And I give a link here if you're not familiar with Jupyter notebooks. Then Jupyter notebooks are interactive notebooks, and Jupyter is spelled with a PY. They are native for Python. You can work with them with other programming languages, and it's really been extended to different programming languages over the last few years, but they're native to Python. So these are interactive notebooks, and they allow us to mock up data and basically do a data science experiment in little to no time. Most of them are going to be cloud-based, and you simply work with them and you run them through a web browser. So there's no additional software to install. So I can start a lab and get students up and running on a Jupyter notebook in basically no time, tell them to browse to this website, and then we're programming in a few seconds. But what's really, really important for us is we have this really rich support for text and for images through the Markdown language. And this includes support for mathematical equations. So we teach them how to do MathJax, which is sort of a subset of LaTeX. And we can then document with rich text with this Markdown language using mathematical equations and sections and all these things like that. And you can really build a notebook with commentary that has exact mathematical equations that dictate and guide the reader what's going on, and then code. Then you would then insert code, work through the manipulation or the analysis of the data, and then you can present it with all sorts of nice plots and everything like that. So it just makes a very nice, tidy way to explain your thought process, show the data, and then show the results and visualizations of the data. And importantly, these are easily shared, and we can version control them. And so that becomes an important piece to this idea with having this open and transparent access. So not only are we logging everything from our connected equipment to a time series database where we're doing timestamps and values, we're also doing a similar thing with how we process data, including the algorithms and methods that students are working with interactive notebooks. And we're taking these notebooks then, and that becomes one of the pieces that would go into the data port as well. So you can look at the raw data, you can look at the marked up data, and then you can really dig into the methods and algorithms used to process that data instead of just the publication or the report. We very much focus on using Pandas data frames for this technology that allows us to do some nice visualization techniques, and we do teach things like dimensionality reduction, clustering, principal component analysis, and we get into regression and time series forecasting. So this notebook approach that we spend most of the time on, the focus is really on communications. We need reproducible connections to the data, and we expect people to have techniques, advanced techniques, but with lots and lots of commenting and really exploiting that markdown feature with equations and everything like that. And the ultimate, or the end result, should be crisp, informative visuals. So conclusions. We're working to create secure channels to bring the data out of the critical infrastructure and then make informed engineering decisions with those. And we want reproducible data and methods that allow any of their shareholders or any of our stakeholders then to get a handle on what was going on with the process. And so we've built this data stack that's based off of equipment and control systems. Then we talk to them using Opc Ua, using secure channels. That goes into Telegraf then, which feeds into our InfluxDB time series database. And then our data processing method being Grafana and Jupyter notebooks. And so with that, I'd be happy to answer any questions. Thank you.